So let's start by going back to the discussion that we had on Monday about inequalities, where we were interested in seeing inequalities from three different perspectives, communicating inequalities using three different perspectives. So I'm going to call these the three modes. Three modes to communicate about inequalities. And the first mode is using an algebraic formula, where I'll say something like x is less than or equal to 6. So, formula. But then we also looked at two others. The next one after that we looked at was drawing a diagram. So, a graph. And if I'm communicating about this inequality using a graph, chances are I'm doing something like, whoops, I meant not to use that symbol. Doing something like writing down a real number line. Maybe I write down some numbers on my real number line. 1, 2, 3, 4, 5, 6. And then choosing to, how would I diagram this one out, by the way? Where would I start drawing this inequality, x less than or equal to 6? Yeah, the way I've usually been doing it is just start over at 6. Am I going to include 6 or am I not going to include 6? I want to include it, and so what do I use here as a symbol that I'm including 6? I want a filled in solid circle to indicate that 6 is a part of this inequality, a part of this solution. And then I just need to shade. And which direction on the number line am I going to shade if I have x less than or equal to 6? I'll shade to the left. And so that would be a graphical way to communicate something about this inequality. And then the last way that we talked about, which we didn't talk about today, but we did visit it on Monday, is interval notation. And so how would I come up with interval notation for the interval that I just shaded on the number line? Great, so the first thing I think about when I think about interval notation is what are my limits, my lower limit, my upper limit. The upper limit for my interval here is 6. So this interval does not go any higher than the number 6. What's the lower limit for my interval? This interval is what we would call not bounded from below. It extends all the way down to what we term to be negative infinity. So it goes all the way down to negative infinity. It goes all the way up to 6. I'll put a comma in between those two things. And now I need a little bit more notation to tell me whether or not each of these endpoints is included or not in my interval. Starting with 6. Is 6 included? Yes, because less than or equal to, because filled in circle. So what symbol do I want here to indicate that it's included? Yeah, I want a square bracket. Perfect. Put a square bracket up here. Great. So that's for 6. How about for negative infinity? Included or not? Infinities are never included because they're not numbers. Right? And so infinities will always have what symbol? Parentheses. Cool. So these are our three ways to communicate about an inequality. Using a formula with an inequality symbol in it, like x less than or equal to 6. Using a graph, a sketch on the number line. I often use these as my intermediate steps. Pretty much every time, probably actually every time, that I've shown you so far how to write an interval notation, I've always used the graph as the intermediate stop in that process. Super important, especially for me, because I have a preference for having visualizations of information. It really helps me. And then interval notation, which is something you can just type that communicates the same information that the other two things do, if it's built correctly. So where are we going next? The next step for us is to try and not just think about one inequality at once, but to think about more than one inequality at once. We want to think about two inequalities at the same time. And so how I'd like to start thinking about that is as follows. So what if we only write down a single inequality like this, whether it's x less than or equal to 6, or x greater than or equal to 1, or x is less than 4, what kinds of intervals are we going to get in that process? if I just write down a single inequality like this, the intervals that I'm describing are always going to be unbounded in some direction, right? I'm always going to have an infinity in my interval somewhere, right? If I just write down x less than or equal to blank, or x greater than blank, right? It's always going to escape out to infinity in some direction. So what if that's not what we want? So think back to our example from Monday. In our inequality example for Monday, we were asking, what grade does this student Rhonda need on her third exam if her first two exams are 78 and 54, and she wants to get a grade of at least a 70 as an average? And we did the algebra out on all of it, and we decided that if Rhonda got anything better than a 78 or better, I should say, on her third exam, then her average would end up being 70 or greater. And that's what the mathematics told us. But then at the end, we sort of looked back in the context and said, well, there's something else that the math isn't telling us that the context probably is. Namely, the context tells us that since she's taking an exam that's probably graded out of 100, that the upper endpoint of this interval, practically speaking, probably shouldn't be negative infinity. It's not possible for her to get 1,000 on this exam. It's not even possible probably for her to get 103. So how did we change this answer in response to the practical context of this problem? Right, so we took that positive infinity and just said, let's get real. Let's just make it 100. Right? And so the practical answer to this question is not an interval that escapes all the way out to infinity, but it's an interval that has a finite endpoint on one end, 78, and also a finite endpoint on the other, 100. So what we need now is we need the mathematical superstructure, infrastructure, whatever, structure, to have that conversation about intervals of the real number line that have both a finite lower point and a finite upper point. Because so far, our single, simple inequalities are not enough to describe a situation like that. So we need to bring more than one inequality to the table. Let's think about that interval, which was the solution of the test problem that we just looked at. So we knew that Rhonda, in order to get the score that she was looking for her average, she wanted her third exam to be a score in the interval from 78 to 100. And why am I using square brackets on both sides when I write this down? So for Rhonda, why am I using the square brackets in this interval notation? What is that saying? Well, so first of all, because it's not infinity, right? So no longer do we not have an upper endpoint. We have an upper endpoint and a lower endpoint. But what do the square brackets actually tell us in this example? If she wants to get a 70 average, is it okay if she gets a 78 on that third test? It's okay. 78 is included in the solution. Is it okay if she gets a 100? Yeah, that's included in our solution as well. So that's what the square brackets are doing. They're saying the number 100 and the number 78 are part of this set, in addition to all the numbers in between, 78 and 100. So if we diagrammed out this interval on the number line, so working our way from the bottom up here, we would have a lower endpoint at 78, an upper endpoint at 100. We would shade everything in between 78 and 100. And then what would I put at the ends of this shaded region to indicate that 78 and 100 are included in the solution? Dots. Filled in solid circles. Yeah. So solid circle there, solid circle there. So there's a graph of this interval. And now here comes the interesting part. So this is the part that we now have to think harder about than we did before. How would I describe, in a formula, using an inequality symbol, those x's which satisfy, or those x's which reside inside of this interval? What are those x's less than or equal to? What are those x's greater than or equal to? So the x's are, so first of all, how do the x's compare to 78? Are they greater than, greater than or equal to, less than or equal to? Greater than. Or because of this filled in circle, it could be equal to also, right? So on the one hand, the x's that we want in this set are those that are greater than or equal to 78. But also, what else are they? Less than or equal to 100. So what we want is a way of combining these two pieces of information together. And the missing link here is that we're missing something in between these two inequalities, because each of these two inequalities, let me take a step back for a second, each of these two inequalities tells us something by itself. Each of these inequalities by itself gives us a part of the puzzle. The inequality in green, x greater than or equal to 78, that inequality, if I were to graph it, gives me a filled-in circle at 78, and then it shades everything to the right. Right? So it doesn't stop at 100, it just goes all the way up the number line. It doesn't have an upper bound. Meanwhile, the inequality in purple here, x is less than 100, that we would diagram as a filled-in circle at 100, and then we would shade everything to the left. And so it also has part of the solution, but it too does not stop. When it goes past 78, it goes all the way down to negative infinity. So clearly we need to do something to connect these two together and say that what we're really talking about is the overlaps. Just the places where the purple and the green sets that are shaded. Just the places where those two things overlap. That's what we want to survive into our orange set. So what we need is a way to combine and look for just the overlaps between these two. And so what we use here is a word. It's not even a symbol. It's a word. It's the word and. So this is when I say that this unit is going to stretch your logical reasoning skills. This is what I mean, is that here, what we're doing when we use the word and is it means that we're looking for numbers that satisfy both of these inequalities. Satisfy both inequalities simultaneously. Right, so a number like 90 belongs to the and of these two intervals because it belongs to the green and it belongs to the purple, right? And so 90 ends up being a part of our final answer. But a number like 75, even though it belongs to the purple interval, it doesn't belong to the green one, and so it doesn't survive into our final answer. So when you use the word and to connect two inequalities with one another, what we end up doing with those two inequalities is just looking for where they overlap. And means take the overlap only. Between those two intervals. And it tends to be and that gets better understood when people are thinking about this for the first time. So if we don't use an and, what do you think its counterpart is? What do you think is the other way that I can take two sets and combine them together? If I'm not using and, what do you think I'm using? Yeah, I'm using or. And it's at this point that it starts to sound a bit like computer science, because this is pure logic that we're talking about here. It's not even really mathematics per se, it's logic. So if I'm taking an or, then I'm not looking for numbers that satisfy both inequalities. I'm looking for numbers that satisfy one or both. One or both inequalities. And so if I decided to OR these two things together, 90 would still belong in my final answer, right? Because it belongs to both the purple and the green. What about 75? Would 75 satisfy this OR? Then it would satisfy this OR, because even though it doesn't belong to the green, it does belong to the purple. So 75 would actually need to be in my solution if these two were joined with an OR instead of an AND. 90 would need to be in the solution. So in fact, if I OR these two things together, how much of the real line will it cover? Give me an example. Maybe I'll ask it this way. Give me an example of a number which will not belong to the OR, which will not satisfy one or the other of these inequalities. Anywhere we go on the number line is going to either satisfy this green inequality because it's greater than or equal to 78, or it's going to satisfy the purple inequality because it's less than or equal to 100. In some places, it does both. But everywhere on the real line, it does at least one of those things. Any number that I choose is going to either be part of the green set, or it's going to be part of the purple set. And so for that reason, if I OR these two inequalities together, I don't just shade between 78 and 100. I end up actually shading everywhere. So then the last thing I want to talk about here is how do we write that using interval notation? This orange interval, which contains all real numbers, what would that look like as an interval? What is its lower endpoint? How far to the left does it go? Yeah, it goes infinitely far to the left, so negative infinity. How far to the right does it go? Positive infinity. And so if we were to write this interval using interval notation, it would be negative infinity to infinity. And what symbols would I use on the endpoints of these in my notation? Always parentheses, because negative infinity and positive infinity aren't numbers, so we can't include them. Great. So what this example hopefully illustrates is that it makes a big difference how we combine two inequalities together. Whether we use an OR connective, as we did here, or whether we use an AND connective, which is what we did back here. When the connective was AND, we were just looking at the overlaps between these two intervals. And when we're just looking at the overlaps, we only end up with this small chunk between 78 and 100, because it's a more restrictive requirement. We need those numbers to satisfy both of these two inequalities. Whereas if we use OR, it's more permissive. Right? There, the numbers that meet this inequality can satisfy one or both. And so we ended up with a lot more numbers in our solution when we had the OR in between than when we had the AND. And my recommendation, I'm going to get you to practice this in just a minute, is when you're solving one of these what we call compound inequalities, right, where it's an inequality, a second inequality combined together with either an AND or an OR connective. When you're solving them, solve each one of them separately so that you get them down into a format that looks like this. And then the fun starts. From there, we need to figure out how to turn this compound inequality down into an interval solution. And as I always recommend, take this intermediate stop by graphing them on a number line. So once you graph them on a number line, then you can either choose the AND and look for only where those intervals overlap, or you can choose the OR, which kind of means to take everything. Glue the two intervals together, and anything which belongs to either one of them becomes a part of the solution.